Hi everybody, welcome to the UW Robotics Colloquium. My name is Dieter Fox, and as many of you know, over the last already 6 years now, I've been sharing my time between the University of Washington and also as leading the robotics research lab for NVIDIA here in Seattle. It's just 20-25 minutes walk here from campus. And I'm really excited about today's talk because we are going to see an update of some of the research that's been going on in the NVIDIA research lab. So there, the focus is broadly on robot manipulation. We're covering all aspects from lower level control to motion generation, high level planning, perception, reinforcement learning, deep learning. And today we'll have a sequence of 3 talks where research scientists from the lab give an update of what they've been doing over the last few months or years as well. The first one will be Kalen Garrett. He's going to talk about task and motion planning, how it can be combined with teleoperation and then imitation learning for robotics. Next, Ankit Goyal will talk about RVT, which is a new view-based transformer model for action-centric manipulation. And last but not least, Ireti Akinola is going to talk about context-rich manipulation and simulation for industrial tasks. So without further ado, let's hand over to Kalen.
Hi everyone, can you hear me well enough? Is the mic on? Okay, good. All right, as Dieter said, I'm going to be talking about integrating planning, teleoperation, and imitation learning for robot manipulation. That we're interested in programming our robots to autonomously solve very complex tasks like this one, where the goal is for the robot to find the spam object and then stow it in the bottom drawer. So here the spam actually starts in the top drawer, so the robot has to actually actively manipulate the world to find the spam using a combination of skills involving picking and placing, inspecting, and also pulling open and pushing closed the doors. This is a very long horizon problem, as you can see, and quite complicated, but we want to be able to use a combination of planning and learning tools to facilitate this. Ultimately, the robot actually automatically infers that it needs to actually place the spam temporarily on the countertop in order to re-grasp it and do the insertion, which is a pretty complex behavior to demonstrate. One way to try to address this is to use the tools of planning, and that's actually how this last video was accomplished. Here, planning has a lot of strong assets to it in that it basically can take a set of parameterized skills, which can be either engineered or learned, incorporating things like motion planners, inverse kinematic solvers, and maybe even neural network graph generators. And it's able to automatically compose them to try to address manipulation for a very large set of manipulation tasks involving variation over initial state, goals, conditions, and even how the task must be solved. But planning also has some drawbacks, and generally you need to actually provide these skills and models of the skills. So that involves constraints governing valid parameters so that the skills are executed correctly, and also preconditions and effects. Many times you need to provide some sort of state estimation, such as pose estimation. And this can be computationally expensive enough where it's hard to run it at, let's say, 30 hertz. In contrast, imitation learning approaches don't have these specific weaknesses, that they're actually quite quick by nature of just being a forward prediction from perception to, let's say, a task-based action. They can run in real time and be reactive to new observations. That they don't require, again, state estimation. They work from raw perception. And by the nature of them, they actually are able to pick up something inherently by the actual dynamics of the system by learning on real or simulated data. But still, these approaches have their own limitations in that they're very data hungry, of course, and there isn't data just sitting around the internet of our specific robot doing all these things quite yet. It often is just difficult to solve the associated learning problems as well, that you have things like multimodal demonstrations. There might be 2 ways to accomplish a task, and these models might average them. That they might have to deal with long and varying horizons, that sometimes you might need to move an object out of the way to open the microwave door and insert something. Other times you might not. And they have to generalize over a very broad state space, which is just challenging in general. So in this talk, we'll talk about how we actually can try to get the best of both worlds of these types of approaches by integrating planning with imitation learning and also a little bit of teleoperation. To start, I'm going to give a really brief background on task and motion planning for those that are unfamiliar with it. Then I'm going to talk about how TAMP can be used to automatically generate data to train these large-scale imitation systems. And finally, I'll talk about how we can actually integrate this and also teleoperation to generate data for more broad distribution of problems and also make more robust policies at test time. So starting with background task and motion planning. So task and motion planning can be thought of a generalization of both classical AI planning, so let's say STRIPS or PDDL style planning, and motion planning, such as sampling-based motion planning, which you might know from RRTs and other algorithms. Really the key distinction from both of these fields is that now we're dealing with a hybrid planning problem. We have mixed discrete and continuous state variables and action parameters. Here might be an example of a planning problem where there's one object, object A, and there's a robot, and the goal is to cook object A. The initial state's defined by the configuration of the robot, the pose of the object, whether the robot's currently holding something, and the cooked state of the object. And the goal is to find not only a planned skeleton, a sequence of action types that can do this. In this case, one simple plan would be to move, pick A, move, place A, and then cook A. But also parameter values for these skills that allow you to actually successfully execute them in sequence. And this involves actually trying to find parameter values that satisfy the intersection of a set of constraints along the plan. That basically every planned skeleton induces a dynamic constraint network of variables, which are circles here, and constraints, which are squares, or rectangles. And we need to find assignments of the variables that are in color that satisfy all these constraints. Some common constraints, of course, are things like collision constraints, kinematic constraints, graph stability, placement stability constraints, continuity of trajectories. And so the goal of algorithms is to find not only this planned skeleton, but an assignment of all these variables, again, that satisfies these constraints. Many TAMP algorithms approach this kind of problem in a two-stage manner, that they do some sort of higher-level search over planned skeletons. Each planned skeleton, again, will induce a constraint network, which we can then describe in a compressed form. And then they try to satisfy this constraint network using a combination of either sampling or optimization-based tools, essentially. In the event that the constraint network is not satisfiable, you have to backtrack, of course. But this is the general gist of a good chunk of these algorithms. Again, one way of trying to address this constraint network is to basically turn it into a directed graph and produce a sampling computation graph, essentially, where at each node in the graph, there's some sampling operation that generates values for the associated parameters that satisfy the involved constraints. And the cool thing about a sampling-based approach to this problem is that these samplers can be black boxes, basically. They can be anything from an inverse kinematic solver to a complicated learning model. For instance, in one project, we actually trained a diffusion model to learn a sampler for how to push open a microwave door from only a point cloud observation of the entity itself. And so this kind of framework is quite broad, and we'll actually see this later on in the talk. So now I'll talk about kind of the first new paper that we've done so far. And so here the goal is to try to leverage TAMP to generate training data for an imitation learning system. That traditionally when people train imitation learning systems, they do things like teleoperation using a joystick controller or a space mouse. But this is very labor intensive, and it might cost you a lot of human time and maybe more importantly money. And so we'd like to be able to automate this process somehow. That one way of doing that is to write a script per each task and environment, but this is really inflexible and also requires a lot of human effort. Alternatively, we propose actually to use automated planning to solve these novel problems and generate demonstrations for an imitation learning system. And really the key idea of why we'd want to use TAMP to train an imitation learning system is that we could try to get the benefits of both, that we can get the breadth of coverage of TAMP, but also lose some of the assumptions, namely that TAMP, again, requires some state estimation capabilities or direct access to like a simulator state, and it's privileged, essentially. But we'd like to be able to operate in the wild off of just raw observations, so just raw RGB or RGBD sensor estimates. And so what we're able to do actually is, in simulation, generate procedurally a large set of environments and tasks, solve them as a task and motion planning problem, and execute a controller to generate different actions. Clean up this data a little bit to remove things that are high-cost traces, and then formulate a large-scale behavior cloning problem to train, again, an end-to-end neural network to demonstrate this behavior. And this is the process we use to train our novel architecture, which we call Optimus, which is a visual motor transformer that it takes in as input a sequence of camera observations from the many cameras that might be in the scene, and then maps them ultimately to end effector pose actions, essentially, at around 50 hertz. So it makes predictions pretty frequently. Again, the outputs here are still poses. They're not full robot commands, so we have to use operational space control to convert them into joint torques. And what we found actually is that this is quite important. So on the bottom left side of this slide, we were able to show that it's much easier for these kind of learners to make predictions in task space than in joint space, especially when dealing with raw observations instead of direct state access. Additionally, another design decision that we made is that we implemented a Gaussian mixture model output layer on this transformer, basically allowing it to predict not just one value, but the modes of different Gaussians to capture some of the multimodality in the data. That intuitively, if you're a planning system, that there are many ways to accomplish some task, and we'd like to be able to characterize them all as much as possible, not just kind of commit to one and then get it wrong.
Is there time for questions?
Sure. Yeah.
I'm curious about the representation that you use here. So when you have task and motion planning, you have continuous variables as well as discrete, like grasp, ungrasp. And how do you encode that? Because that's a measure zero set, right? Whether you grasp something or not.
Yeah, so it could be a function. I mean, even if it's measure zero, you can still have a function that says, I mean, in the real world, it's not really, I guess, right? But you can map that continuous raw state to some sort of discrete dynamic about contact, right? Like whether contact is on or off, essentially, right? So that's how you do it in a TAMP system. And it is a little bit of an approximation from a modeling perspective, but that's...
And yet it is able to learn that joint discrete and continuous.
So this is not going to learn how TAMP actually plans. It learns to reproduce the input-output contract of the TAMP solver. So this has no semantics of anything that's like a state variable or an action. Yeah.
I'm just like impressed that it is able to, since I can imagine mathematically this working in like continuous spaces, but I'm impressed that it's able to deal with these sort of.
Right. I mean, the underlying input-output contract's all continuous, right? It's images to some sort of command that's continuous, right? I guess, and also in this case, how we formulated a gripper command.
I guess like there is some squishiness that you're adding that allows you to do that.
Yeah, I mean, it's
like between the difference between not grasping and grasping is infinitesimal in state space.
Yeah. No, it doesn't even use the contact in its observation. It just uses the joint position of the fingers, right? And so this also, by being a transformer, has history, which is like critically leveraging probably to actually infer whether it's holding something.
Yeah.
Do you have to change anything in your TAMP problem to make things more or less learnable? Like, are there particular solutions that are easier to learn versus harder to learn?
Yeah, so one thing that's important is to try to produce kind of high quality demonstrations, to really try to run it in anytime mode and minimize the cost of the plans found, right? So that actually tends to be quite useful. I'm not going to talk about it too much today, but there are some kind of small things like that are pretty important. Also, again, I think even with the Gaussian mixture model output layer, multimodality is still an issue, that there are things like diffusion policy that might be better at capturing it that we could try these days. But we have to think a little bit about how do we actually reduce the variation, because still with this kind of model, you have a finite number of modes that you have to pre-specify, right?
Are there other silly things like if your trajectory is like wait for a while, then it like totally confuses your imitation learning?
If it's Markovian, yeah, definitely. Yeah. That definitely came up, yeah. All right, I'm going to keep going out of the interest of time. But we were able to show it on a kind of distribution of procedurally generated tasks with varying manipulable objects from ShapeNet. And it's able, again, for each of these, we basically solve it as a TAMP problem, generate a data set. And then when testing on a new unseen distribution problems, Optimus is able to do pretty well. And we have some numeric results that kind of show this, that first, this transformer architecture improves on kind of baselines that are both non-recurrent and also recurrent, so like an RNN version in particular. And then interestingly enough, actually, the learn policy outperforms the TAMP system, both in terms of runtime, but also in success rate, by virtue of training only on the successful tasks that we're able to actually have better performance overall, which is, I think, quite interesting. And then maybe from a TAMP perspective, the most interesting thing is that we're actually able to show that the network is picking up a little bit on reasoning about like collision avoidance, that here this little crate object starts on one of the platforms. Sometimes it obstructs the door, sometimes it doesn't. For this example, it obstructed the door, so the robot had to move it, but here it doesn't. And the network is able to pick up on that and then choose the higher quality, or choose a lower cost behavior by just opening the door without moving it whenever it's not obstructing. Again, this demonstrates some kind of robustness to the variance and horizon that might come naturally in these kinds of problems.
Again, like to your point about the results there, I guess TAMP, it is able to outperform TAMP because it is faster. You're giving them all the same amount of time and you're measuring, because TAMP is I guess, it is probabilistically complete, right? So it will eventually find the right answer. But you're saying here that given the same amount of time, your algorithm finds solutions faster than.
Right, and you could imagine amortizing the TAMP cost a little bit in some strategies to make it a little bit closer. So here,
Mostly curiosity, not any.
No, yeah. Again, this is not, the tasks I've shown are not maybe the most broad distribution that one could imagine. So I think there's still a lot of room to improve on these models to make sure they truly cover every problem. This is also task conditions. There are separate policies being learned per goal, which is limitation, but that's something we'd hopefully relax in the future.
For clarification, I'm not sure. Are the failures of the TAMP system all due to, let's say, planning timeouts, or are they also because it just couldn't pick up an object or things like that?
Yeah, so they're both. So there are planning failures. Sometimes the problems that are generated might even be infeasible, right? So if something's just a little bit too far, then it's hard to tell without a timeout or something, or at least guess whether it's infeasible or not. But also, yeah, we're using these ShapeNet objects, and we have GRASP computed from something called the acronym GRASP Database Online. And the GRASP might not be that good for this simulation tuning, essentially. So some of them will fail naturally, and that's not baked into the planning model per se, right?
Like the video you just showed, a couple of the iterations, it seems like the robot arm like kind of almost, it looks like it froze for a second without holding anything, just like sitting there, almost like it's thinking. Why was it? Why is like a behavior like that?
I think it's imitating something where it's moving very slowly, and so the learner is actually kind of screwing up a little bit and making that roughly a zero action. But again, the history allows it to eventually recover from that. I think we could do a little bit of cleanup with the training and also the learner to try to reduce that effect. And finally, in the last, let's say, 3 or 4 minutes, I'll talk a little bit about this last direction, which is that this PASS system, although it's able to generate data in an automatic way, it still assumes they're able to model it in a way that a TAMP can solve. And this might be a little bit challenging for problems that have contact-rich segments. For example, if you're trying to prepare coffee, and you're trying to stow maybe the coffee pod in the coffee machine, that might be kind of a low-tolerance skill that you need to actually deploy. One way to actually get around that is to basically leverage teleoperation and use that as an implementation for a skill, that we can treat this whole problem still as a TAMP problem, but where we get to something like an insertion, deploy a human to actually do that for us, essentially. And then basically this gives us now a shared autonomy system for both collecting training data and also maybe just controlling robots in general. And one other observation we made is that not only can we use this at training time in order to, again, in a semi-automated fashion, gather a bunch of data to train an imitation learning system, that we also can use this at test time, that we can replace the human with our learn policy trained on our data to get a fully autonomous system, again, when deployed in the wild. And so the way this would go, just to back up, is that you would gather data here in this little example where the human would teleop the insertions, but TAMP would do the rest. And TAMP basically is getting you close to the insertion point. We get a bunch of that data, we train our policy, and then now we replace the human with the learn policy. There are a couple technical challenges to actually doing this. Really, the key one is the modeling aspect that I talked about before. It's that we want to be able to characterize the skill of a human teleoperating something. So we need to understand kind of the preconditions in particular for this. In this case, if you're doing an insertion, we want to understand the distribution of poses of the tool and the stand when trying to do the insertion. But what we can do is we can bootstrap that set from an example number of distributions that's really small, let's say fewer than 5, and then basically put that into our planning model in order to be able to model the capabilities of a human. Additionally, one other thing we can take advantage of is that now that we have this system that's mostly autonomous, but not fully, the human's idle whenever it's not, whenever the TAMP system is working, right? And so it's kind of a waste of the human's time. Instead, what we can do is we can try to, in simulation, spawn multiple environments with multiple robots and have the human alternate between them in a queue-like fashion, where basically these TAMP systems are sending requests to the human to do control on certain segments that the human then will accomplish in sequence. This also can be deployed in the real world if you're a human supervising a factory, right? That you can imagine having a fleet of 5 robots and having the human handle really the fine-grained nut assembly components of some sort of task. We were able to kind of validate some of these expected insights with some experiments. First, we were able to show that our system as a data generation tool is able to be much more efficient than conventional data generation with just brute force teleop. We surprisingly found that the data produced by our system was actually higher quality in that it led to training policies with higher success rates than just a brute force teleoperation data set. We think that's because the data has some regularity to it, that it's using planning, so it's less jittery and stuff like that. then finally, at test time, if we combine teleoperation and planning, we're able to achieve the highest success rates, both when we use our own data and also conventional data, which shows that, again, compartmentalizing these learning problems and using planning for the aspects that we understand well is actually quite advantageous. And here's an example of this in the real world on this tool hang task, which is quite challenging. One additional advantage is that although the TAMP part needs some state estimation, it can be really crude because, again, a lot of the fine-grained control is being handled by the imitation learning agent. And so as long as we kind of get the rough vicinity of where to start for this kind of hanging and also insertion phase, then we are in good shape. And that wraps up my talk. Just to summarize a couple key points. So first, imitation learning and planning kind of have complementary strengths and weaknesses, but we can use them together both in terms of our deployed policy and also in terms of our preparation of our policy. That we can plan with TAMP using both learned and engineered skills to do things like incorporate neural networks and also model the effects of other agents, such as a teleoperation agent. TAMP can be used for automatic data generation quite flexibly. And then finally, again, we can use these hybrid systems both at data generation time and also at deployment time in order to improve our efficiency and overall robustness of our behavior. All right, thank you.
So I'd say, just for the organization, I guess, right? Maybe we have main discussion at the end, but maybe now at the switch off, maybe one quick question. Yeah.
So, how many times does it happen, or does it ever happen that your policy outputs certain sort of task-based commands that your lower-level controller can't follow, or does it adapt to it?
This is one of the key challenges of imitating a TAMP agent that works in joint space, that it has more control affordances. So sometimes, I think for some of these tasks, that they're kind of easy still because they're mostly tabletop. But if you imagine like reaching into higher cabinets, that would come up much more often, I think, and I think it's no problem. Good point. Yeah.
Okay. Hi everyone, I'm Ankit, and I'll be talking about our work RVT, Robotic View Transformer for 3D object manipulation. So this work was done at the robotics lab and with awesome folks like Jay, EG, Vals, Uwe, and Dieter. So here we are focusing on the task of 3D object manipulation. So these are tasks that go beyond like usual pick and place. So for example, here these tasks involves like opening drawers, putting things inside drawer or hanging cups. So these are the tasks that we are focusing on, and this is like a fundamental task in robot learning. So in general, to solve these tasks, there are two kinds of approaches. So one of them are like view-based approaches. Essentially, these approaches just operate on the 2D images. But the issue with these are, so these are generally very scalable, but they cannot handle like 3D manipulation tasks because they are more suitable for things on tabletop and moving things on the tabletop. On the other hand, there are a new set of approaches which actually model reason in the explicit 3D space. For example, PARACT, which was a work at UW by Mohit. Here, these approaches model the explicit 3D of the scene and reason with the explicit 3D, and they tend to perform well. But we find that they are not really scalable, and I'll go into the reasons. With RVT, our objective is to make something which is both scalable and like works as well as other 3D approaches. So I'll just give a very quick overview of PARACT here, which will help us understand RVT. So PARACT and these kinds of methods fall into this category of key point based manipulation, where the system works in key points. In the sense, given a current observation, it predicts like a key point where let's say the gripper has to go. For example, here the key point is right above the. For example, for the task is put the tomatoes on the top bin. Then the first key point would be something right above the vine of the tomato, and then the next key point would be something so that it can grasp the vine, and the third key point could be something right on top of the bin. So here, the execution would be something like the system takes the current state, it predicts the next key point, the robot goes there and then proceeds. in this fashion. So this is what Paract and similar approaches do. Now, in terms of the architecture, what Paract does is it takes as input the voxel of the environment. These voxels are then tokenized into tokens. So since it's taking voxels, it will do something like resolution cube number of tokens, and then it processes these tokens to predict like this heat map of location where the next key point should be. So this is like something at a very high level what Paract is doing. And when Paract came out, it significantly outperformed the prior methods that existed before. Now the question is there a way to avoid the cubic cost associated with processing voxels? Because you can see the voxels are cube with respect to your resolution while preserving the 3D information. And that was the question that we were thinking about and proposed RVT. So let me go into what RVT is and how it's doing this. So the input for RVT is the same as Paract. So you have some bunch of real world observation and some description of the task. From the real cameras, the first step is like you create like reconstruct the point cloud of the scene. And once we have the point cloud, the key insight is that we place virtual cameras. So these are cameras which are not present actually in the scene. So these are just rendering the reconstructed point cloud into various orthogonal locations. So these are virtual cameras, and we render the scene across these virtual cameras. And we, along with rendering the RGB, we render multiple channels. So there's a 3D coordinate channel which essentially renders the correspondence information across the channels. We render the depth. So now we essentially model all the 3D information through this multi-view channels. And then all these images and the channels are fed through like a transformer network. So we reduce the number of tokens, which was essentially cubic before, to square of resolution now. And we also use the task instruction, same as Paract. And the prediction essentially is a position heat map for each of these channels. So we will have like a position heat map of all these channels, and these position heat maps are then essentially back projected into the space. So for example, these 5 locations are back projected to give you like the target location. So by this operation, we can model the same capability as Paract, and we find that with this method we can achieve higher success rate, faster inference, and much higher training speeds. Yeah.
Is there ever an issue of the hotspots of the different 2D images not corresponding to a single point in 3D space?
Yeah, that's a good question, and it could happen. But we find generally we generally find like success. So they generally kind of agree. And if there is, let's say, a confusion in one of the views, so we expect the network to give like to give that confusion, and then it gets resolved through the different views of choosing. Yeah, so we were able to achieve much higher success rate, faster training speeds, and inference with this model. And here, what I'm showing is that it's the same network which is trained for all these tasks, and it takes like just 10 demonstrations, and it gives a relatively high success rate in the real world with just 10 demonstrations per task. But here are some of the failure modes we observed for RVT, especially with markers. We find that it was at times unable to differentiate the color of the markers and had like grasping failures. So here are some of the failure modes.
Quick question. Like, what's your guidance on choosing the number of views and how they're positioned?
So the virtual views, we keep it fixed. So those are 5, and those are 5 around the workspace. And the input view is just one third-person view of the environment.
And like, how do you decide where to put them?
Yeah, so we define like a workspace. So let's say that's 1 meter by 1 meter for the robot, and then we put it such that we render everything in that 1 meter for the cube. So we put it at, let's say, 2 meter distance such that it has a 45.
I was just maybe quick follow up, and then I want like if you had to add another view, where would you put it?
And also I would put it near the wrist camera or something which is like a closer view to the object of interest. And so.
And maybe one quick comment. What we're seeing right now is, I mean, for these scenes that are kind of tabletop, it makes sense maybe to place them at these locations. But if you have the robot that should, for example, grab something that's inside a drawer or something like that, then you might want to consider rendering views that kind of look into the drawer, right? Then rather than these fixed off of the ones. So there's flexibility.
Yeah. So so to go to summarize, essentially. So this is like a general method for 3D manipulation. We find it more scalable and accurate. And the key insight is it's trying to avoid the cubic cost associated with processing voxels while preserving the 3D information through virtual views. It tends to work well with just 10 demos per task, even in the real world. And I think one of the current limitations is like handling thin objects and generalizing to unseen objects. So these are like some of the things we are working on with like future models. Cool. Maybe I can take questions at the end, or if there are any quick questions.
My name is Ireti, and today I'll be talking about how we leverage accelerated simulation to learn robot assembly skills in the virtual world, and how we can deploy those skills onto the real robot. So I'll be discussing this in 3 phases, essentially answering 3 questions. How can we efficiently and accurately simulate contact-rich interactions? Because those are important when you're putting parts together for assembly. How can we use the simulator to train robots to learn the skills in a useful way? And how can we transfer behaviors that are learned in sim onto the real world which we care about? And this work I'll be looking at this through the lenses of 3 works. One is titled Factory, which was presented at RSS last year. The second one is Industrial, presented at RSS this year. And the third one is a follow-up work which extends the prior works by improving their robustness to uncertainty in the environment. So let's dive right in. How do we efficiently and accurately simulate contact-rich interactions? For this, we look at the nut and bolt interaction as our case study. And this is because 40% of assembly operations in industry entails nut and bolt interaction. So this is a quite ubiquitous task. Another reason is because prior works have found it hard to simulate this interaction at real time. So technically, it was an interesting problem to tackle. And there are a few strategies that enable us to be able to simulate it faster than real time. First is STF-based collision, doing a contact reduction scheme, and using Gauss-Seidel solver. And I would go into these in more detail in the next slides. So to understand what makes the problem hard, you can look at the geometry of the nut and bolt, and you would realize that the threading contains a lot of intricate geometric details, which when you look at, for example, the mesh models from a CAD model, you can have as many as 50,000 elements to be able to accurately capture the geometry in the object. And this can be quite challenging for a physics solver because that entails computing the contact locations, computing contact normals, and enforcing interpenetration constraints, which scales by the number of contacts that you generate. So a key insight that we use for this work is that rather than represent the object as meshes with tens of thousands of elements, we represent them as signed distance fields. So which is the mapping of every point in space as a distance to the boundary of a given object. And this way, we can, for any object that we are simulating, compute the signed distance field representation on a dense voxel grid. And during simulation, when an object A is approaching, say, an object B, we can very quickly query the distances of points on the surface of object A relative to the signed distance field of object B. So that way, we can very quickly generate contact locations as well as contact normals. And with that, we are now able to simulate the nut and bolt interaction at real time. Now, that was good, but still not good enough for robot learning, because for robot learning, you need to be able to generate a lot of data in parallel, faster than real time. And we had to take that on as well. And to understand the bottleneck here, you'll notice that because of the detail in the geometry of the object, during contact interactions, you generate a lot of contacts, sometimes as high as 16,000 contacts. And the key insight that we use here is that we perhaps do not need this many contacts to simulate this interaction in a physically plausible way. And what we did is to come up with a contact reduction scheme that helps us do some form of clustering to reduce the number of contacts to 300 from 16,000. So using different types of solvers, we see massive speed-ups in the number of environments that we can simulate in parallel because of this contact reduction scheme. So for example, for the Jacobi solver, we can go from simulating 20 nuts and bolt interaction on the desktop GPU to simulating over 1,000 nuts and bolt interaction. And that way, we are now able to simulate thousands of nuts and bolt interactions at the same time on desktop GPU. Question?
So the signed distance field for the bolt itself, is that a formula, like an algebraic formula, or what's the representation?
So it's for every point in space, you can compute the distance to the closest distance to the mesh. So this is
So it's just a numeric representation.
It's a numeric representation. Okay. So, and it's important here what the resolution is. So you have a voxel grid, and for every point in the voxel grid, you compute that.
The voxels out of something more continuous. I see.
No, it's just centered around the object itself. So once we can simulate the contact-rich interaction, we can bring robots into the scene and now simulate the complex manipulation interactions that is useful for the robot to learn. Here, I'm showing the nuts and bolts being fed, the nut being fed, and the Franka robot picking it up using a scripted policy to thread it onto the bolt. So now that we're able to simulate that interaction, the contact interactions, we need to learn the skills for the robot in simulation. And to do that, we have a number of strategies, and I'll discuss 3 of them. First, with contact-rich simulator, you can import whatever relevant assets that are important for the task that you have at hand, and you can create learning environments to train robots in simulation. So for example, on the left, you have the nut and bolt environment that has a nut starting on the table, and the objective of that particular task is to get the robot to pick the nut, move it onto the bolt, and thread it all the way down to achieve the goal state. And similarly, you can create other environments, such as the insertion environment, as well as the gear assembly environment. So once you have the training environment, then you have to reason about the algorithm that you want to use to solve it. For this work, we use reinforcement learning, perhaps essentially because it's been found to be very useful for solving other robotic tasks aside from contact-rich tasks. The challenge of contact-rich tasks when using reinforcement learning is that contact-rich tasks can be quite long horizon, and for reinforcement learning, where you have to do a lot of trial and error and exploration of the environment, it can be challenging to stumble on good behaviors for such long horizon tasks. So one decision that we had to make is to decompose the task into subtasks which can make the exploration problem easier for the reinforcement learning algorithm. So in this case, we use domain knowledge of the task to split it into reasonable subtasks, pick, place, and screw, and we learn policies for each of these subtasks, and then chain them together for the full task. So using reinforcement learning, you have to define what the Markov decision process is, and essentially we use observation space here to be the poses and velocities of objects being interacted with, as well as the proprioception of the robot. For action spaces, we tried 2-dimensional action spaces versus 6 degree of freedom action spaces. We implemented a number of different controllers and tried different gains. In simulation, you can carefully try out different things and see what works and what doesn't. And for the reward function, we use post-based reward or key point-based reward to learn the task. So this was defined for each of the subtasks to come up and learn policies for them. And then once they're learned, we can then chain them together. So ultimately, the success rate of each of the subtasks were, for this easier task, near perfect, but for the screwing task, about 90. And then by the time you chain them together, you can still have a fairly reliable system to do the knot picking and threading task. One important algorithm that I think is valuable for context-rich policy learning is the simulation-aware policy update. And the thinking here is that nearly all context-rich simulators have some form of error in them. And the error manifests itself by a level of interpenetration between the objects in the environment. And the key insight here is to make the policy update process aware of this potential error in the simulator. So for example, on the left here, I'm showing a histogram of the interpenetration distance in our simulator, especially early when the robot is aggressively exploring the environment to learn the task. And what we do is, for each episode, we compute the maximum interpenetration depth, and we throw away episodes that have the depth above a particular threshold. For the remaining one, we can scale the returns of the episode to penalize episodes that have a lot of penetration depth. So that way, over time, the robot learns to explore the environment in a way that minimizes interpenetration between the objects in the scene. Okay.
So is this sort of biasing the search towards solutions which are not going to excite dynamics, which are hard to model, or is what kind of the solution here?
Yeah, it's to bias the search to not break the simulator. So, and also it's also good when doing sim to real, because you don't want the robot to be too aggressive when performing the task in real. So it has that advantage when doing sim to real.
I have a question.
Yep.
So what you're fixing is essentially model misspecification, right? Like when there's a lot of contact, there's model misspecification. You're trying to like stay away from the points of misspecification. Right?
Yes. So that's a part of it. Another is to induce more delicate behaviors, because if one way reinforcement learning would exploit the simulator to come up with different strategies. There are different strategies to solve a task, but some solutions are better than the other. And here we're using this approach to incentivize more delicate behavior. One other challenge is that contact-rich task, you want contact to do the task. At the same time, you don't want too much contact, for example, when dealing with delicate objects and stuff.
So just penalizing contact forces be equivalent?
Yes, it would. It can be, but contact force is going to be a specific, a number, but interpenetration distance can occur anywhere in the object. So, So contact force can be a proxy, but I think interpenetration depth covers the.
You could penalize interpenetration depth, like as in, there's no need to filter the episodes and stuff. You could just like change the cost function and kind of get the same.
Yes. So what we're doing is that we're doing some filtering, and at the same time we're also doing some penalization on some that are not so yeah. So now we have the policies trained in Sim. We want to deploy them on the real robot. And when we tried it, we encountered a number of challenges and came up with a number of solutions to address them. So I'll discuss them in order. So what could possibly go wrong? First thing is that when you're dealing with industrial assembly, you have to deal with objects that are small and are very reflective. And this can be very challenging for a lot of vision-based systems. And remember, our policy takes in pose as input. So we depend on good pose estimators to get the pose of the object that is to be interacted with. In the middle, I'm showing the raw point cloud that goes into the pose estimation system. And you can see how noisy this observation is. So even for state-of-the-art pose estimation system, they're still going to struggle to come up with perfect pose estimation.
Do you just use like regular cameras, like webcams, or do you use like LiDAR?
We use Intel RealSense D435. So it has both RGB and depth, but popular in research-grade cameras. Yeah. So essentially, we need a policy that is able to handle this sort of observation error. Another issue is the dynamics mismatch, and this can happen in different flavors. For example, on modeled joint friction and damping. As you use the robot, the joint friction and damping changes over time, and they can be very hard to measure. Modeling that in SIM is quite challenging, and we need to be able to handle that. Also, sometimes the controller implementation and specification in SIM might be slightly different from what you have on the real robot, and you need something that can handle this sort of gap. So here are a few ideas that we use to address some of these challenges. So first, for pose estimation error, we use observation noise, and we essentially make sure that the noise is large enough to capture the distribution of the measured pose estimation error that we observe on the real robot. For dynamic mismatch, first we use system identification to obtain a good estimate of the joint friction and damping. And the way we do that is in real, we move the robot through some free space sinusoidal motion. And then in SIM, we can optimize the parameters to be able to obtain motions in SIM that largely match the motion that you generated in real. And once you do that, you have an initially good estimate that you can use domain randomization over that during training in SIM. Sometimes you have observation mismatch. So for example, on the real robots, we observe that the joint velocity information can be quite noisy. So compared to the SIM, where it's very, very smooth. And one approach that we do is that we only use reliable observation inputs in real. And because we're doing reinforcement learning, the critic in SIM can still learn from having access to the other observation modalities that are readily available in SIM. So on the left here, I'm visualizing what the observation noise looks like in SIM when learning. So the input to the policy is shown in red, and the agent in simulation learns to be robust to this sort of this level of observation noise when learning the task. And then using these and some of the elements that I mentioned earlier, we're able to now fairly reliably deploy the policies trained in SIM onto the real robots. So checkpoint. So now we can simulate contact-rich interactions at a fast rate that enables us to generate data for data-hungry algorithms. We can then use that to train robots for robotic assembly skills, and we have a recipe of how to transfer skills learned in SIM to the real robot. So what next? So far, the policies that I've shown depend on pose information. And the pose information is obtained at the beginning of the episode. So afterwards, they cannot update the pose information of the environment. So this means that it can be difficult for them to be adaptive to disturbances in the environment, which is a problem. Also, the agent does not use any form of force feedback or tactile sensing information. And the way we humans are robust to such disturbances is that we use different perception modalities to compensate for depending on the disturbance that we experience. tactile sensing is a good modality to do that. And taking the simulation-first approach, we've built also a very fast tactile simulation environment that enables us to use similar techniques that I have described earlier to learn tasks in SIM. Now, on the left, you're seeing an insertion task using tactile sensing. In the middle is a peg placement task. So these are rotation-heavy tasks where the agent relies on the tactile information to determine how to place the peg there. And then on the right, you have the not bolt screen task. We are also able to deploy the policy on the real robot. So for example, here is a peg placement task where the robot reactively places the peg in an upright way, purely using the tactile information that it is getting from the tactile sensor. This has been a multi-team effort with a lot of collaborators from the simulation team and from researchers at the Robotics Research Lab led by Dieter Fox. And I would like to acknowledge everyone. Thank you very much.
Yep. Should we use the microphone? So it can be a question for any of the phones.
Thank you. I'm actually really curious. So you said you used like the RealSense camera for the real world,
yes.
Look into errors, because I actually used the same camera, exact same camera
yep.
brand. Like in my research, I was wondering if you did anything like in terms of like processing the data, because like that's like mostly what I kind of experienced was like yeah. I saw the ripples on a reflective surface. I kind of did like a low pass filter. I was wondering if you did stuff like that.
We have some vision researchers that we collaborated with, and a lot of effort went into, for example, tuning the parameters of the sensor for exposure level, the dynamic range of the sensor to improve the quality of the output, and we also do some filtering, like you said. Mm-hmm. But still, because the object that you're dealing with is inherently challenging because they're metallic and reflective, you will still have, it's hard to get a perfect, for example, point cloud information from such. One approach would be to buy more expensive cameras because those ones are designed particularly to handle these sort of scenarios. So, you can make an effort to tune it as much as possible, and then you have to develop systems that are robust to that. Yeah.
Sounds good. Thanks for the insight.
Thanks.
If I ask one more?
Yes.
I actually want to ask for all three of you guys. I was wondering if you guys, what's the word? Like for like projects, you guys like work with each other, talk about projects, because it seems like for the first talk, you like the tasks that you need to put in a human in the loop are these precise, like contact-rich tasks, like screwing a nut on a bolt. So I'm just wondering if you guys like ever talk about that, like incorporating each other's research into.
Yeah, I think it's one of the larger focuses in the lab nowadays that we do have these separate projects, but there's a lot of room to try to make a holistic robotic system that uses all of them. One example of this is actually that some of the data I showed to train imitation learning systems is being used to generate data for RBT, right? So I think there are a lot of opportunities to try to combine these things, as you suggested.
Thank you.
So you said you were doing system identification mostly for like friction damping parameters using real world data. And so to understand you correctly, when you're doing the reduction of contact points, is that mostly just like based off of your simulation models? And in particular, do you think there's room to sort of use real world data to sort of pick which contacts are the most important when simulating? And yeah. That's
a good question. That's a good question. So currently, the contact reduction scheme is based on the clustering algorithm that helps the solver to work fast and also reduces the interpenetration as much as possible. Now, the interpenetration that happens during learning is different from what. So, for example, when simulating nut and bolt interaction, without the robot, the nut would always respect the interpenetration constraint. But when learning with a robot in the scene, the robot is exploring using reinforcement learning. So it would naturally apply perhaps large forces that would push the limits of the simulator. And that's why we do the additional step of informing the policy during training about the potential error. So in general, given enough time, the simulator would solve the interpretation constraint. But for the learning purposes, you have to balance the amount of time you give the simulator to solve for the constraint versus come up with ways to speed it up as well.
We had several questions during the presentations already, so thanks a lot, everybody.